right. Good morning, friends.
Good morning, everyone. So great to have you back at Field Trip Fridays. I'm Jenna.
And I'm Steve.
And we are super excited to learn more about today battery chemistry with the Warren Lab at UNC Chapel Hill. And so we have Lauren and Madeline with us. Welcome to our fun Field Trip Friday broadcast, Lauren and Madeline. Good to see you again. Each Friday, we're hosted by a different DPS classroom, and hopefully one day, your classroom will be a host one day. This week, we have Miss McLeod's third grade class at Parkwood Elementary. Shout out to Parkwood, my friends. Woohoo!
Parkwood!
Yeah. Hopefully y'all can see that photo of Parkwood. There's your school. That's the best one I could find.
So for those of you who are joining us in Zoom today, I just want to let you know that while we're watching our video, you can ask questions and make some observations in the chat, and I'll be in the chat too. And so will Lauren and Madeline to answer some of your questions. And then after our video, we will be able to have a live Q&A with Lauren and Madeline. Steve, should we get started?
Yeah, let's do this. I'm so excited to share this trip with you. It was so fun. Jen and I had an amazing time learning so much from Lauren and Madeline. I hope you have lots of questions, and we'll get to those when we're finished. Let's watch. All right.
Hi everyone, I'm Jenna.
And my name's Steve.
And welcome to another Field Trip Fridays. Where are we today, Steve?
We're at the University of North Carolina in Chapel Hill, and this is the Keenan Laboratories building. We're going to be visiting the Warren Lab, where we'll meet Madeline Stark and Lauren McCrae. They're graduate students, they're chemists that work on making better batteries.
Cool, let's go check it out.
Let's do it.
Hey Lauren, hey Madeline.
Hey y'all.
Hey. How's it going?
Good.
Cool, so can you tell us a little bit about who you are and what you do here at your lab?
So I'm Lauren McCrae. I'm a third year PhD candidate in the Department of Chemistry at UNC Chapel Hill. And I work to computationally and experimentally explore new materials that have applications in batteries.
Cool. So that means you do experiments both like kind of on a bench, like in a laboratory, but then you also do kind of analysis and experimentation with computers?
Yes.
Yeah,
Cool.
I'm Madeline. I'm a fifth year in the Warren Lab, and I'm looking at taking materials for battery applications and characterizing them using different techniques to make sure that they're working and to see how we can maybe improve those materials.
That's really cool. What is an arc welder?
So basically it runs an electric arc through the chamber here, and when the copper hearth is up there, it acts as either the cathode or like as one electrode, and this acts as another electrode. And when you strike an arc, basically you touch the tungsten tip to the electrode, the copper hearth, and it creates an electric current that's really concentrated, so it'll get up to 2,000 to 3,000 degrees Celsius in the chamber, and it can melt really high melting point materials.
cool.
And so, yeah, so typically when we do it, we'll put up the copper hearth into here, and it kind of just sits up in there. And we will flush out the chamber because it has oxygen in it. We'll flush it out with argon and vacuum. And then once we're positive that this is an argon atmosphere, we'll keep it at positive pressure. We tend to keep it around, I think, 15 to 20 kilopascals of argon atmosphere. And then we will turn on the electric the electricity will strike our arc, we'll try and melt our sample, and then we'll let it cool down because it gets really hot. So then we take it back out and we'll take it into the glove box, and we hope that we made what we were hoping to make. So now that I'm in the glove box, I can manipulate everything in here, and this is the ball mill.
So this ball mill shakes.
It shakes. So we use it, I don't know that I have a ball mill jar in here now, but I can, oh yeah, we do. So we have a jar. This one's covered by Kapton tape because we close it with tape. But this is the size of the jar, and it has a top on it, and it's a stainless steel jar that has a little mini ball in it. And so you put the stainless steel ball in this little stainless steel jar with your material, and when it shakes, it breaks up the material into smaller pieces. And so we basically use it because sometimes hand grinding, if our materials are really hard, sometimes hand grinding doesn't work. And so this will allow us to grind it into smaller pieces than we might be able to by hand.
Why do you need your materials in small pieces?
So typically in solid state reactions, you're reacting multiple solid materials together in order to get them, or you're putting them together and trying to get them to react in the solid state, right? And so surface area is really important when trying to get them to react, because if there's more surface area that's interacting with one another, there's more likelihood of a reaction occurring. And so if you're able to get them into smaller pieces before your reaction starts, it could make the activation energy, or the amount of energy you need to actually get the reaction to occur, it brings it down. And so it makes that reaction easier. And so some people actually use these ball mills to do reactions, because sometimes the energy that you get from just shaking them will give them enough energy to react.
Cool.
Most reactions you need to bring up to a higher temperature, which is why we do high temperature solid state reactions. So this combined with the high temperature can allow you to overcome that activation barrier, or give you enough energy to get the reaction.
So cool. Yeah.
That
Because
is
basically
really
what
cool.
you're doing is you're using these tools to create reactions that are difficult to happen normally.
Yes.
Under normal conditions, these chemicals wouldn't react, and you're kind of pushing them to react with one another.
Exactly.
Great. Cool.
So that's what it looks like. And so you're running both hydrogen and oxygen through there, and you're basically getting a combustion reaction that's producing the fire. And then we use it to seal quartz tubes like this. Because quartz has a really high melting point, so this is an open flame that's somewhere between 2,500 and 3,000 degrees Celsius. And so it gets hot enough in order to melt the quartz, or the quartz, and seal it.
So I know you put in certain reactions and you heat them up so that a reaction occurs, right? So why do you need heat for a chemical reaction?
So, term that chemists would use is kinetics, right? And so you need to overcome an activation barrier in order to go from reactants to products in a chemical reaction. And typically that activation barrier is higher energy than either your reactants or your products. So you have to give the reactants energy to overcome that activation barrier. Heating them up is one way to give your reactants energy to overcome that activation barrier. And so for us specifically, typically the way that our reactions work is you get close to the melting point of your reactants. And so if one of your reactants is close to or at the melting point, it might start to go into the liquid phase. And again, increasing surface area, the amount of molecules or the amount of molecules that are coming into contact with one another, that helps you overcome that activation barrier.
Once we've made our materials, we want to be able to do reactions with them. And so we can put them in devices like this that we've assembled, and we want to do electrochemical reactions. So essentially, we will put down our material on one side that's conductive, and we have a wire that's connected to that, and then we'll have other electrodes on this side, and we'll be able to put in our electrolytes. So these are going to essentially be like ions that will go into our material and charge it and discharge it. So this will be like what happens in your cell phone batteries or something like that, where you'll have ions moving in and out.
And that's how charge is kind of in the battery or not in the battery.
Not in the battery.
Exactly, yeah.
So, and then using this device, we can actually look at how those ions are moving in and out while it's happening. So we can actually monitor the chemical reactions that are going on.
Cool.
And what we can do is look at it under an optical microscope. And so essentially what we'll be able to do is watch what's happening to the material when the ions are going in and out. So we can put it under an optical microscope, and we will hook it up to a potentiostat. So this will be able to apply a current that will shove the ions in and out of the material. And so what this will do with our optical microscopy is let us look at any color changes or just how the material is changing when our ions are going in. So
I have a question for you, Gawan.
Yes.
So what is the significance of a color change?
So that's a good question. So what a color change will tell us is it'll tell us about how the material is charging. So when you add electrons or take electrons away from your material, that will change the light that it's absorbing and reflecting. So the graphite starts out as gray, and then when we take electrons away or add them, the color will change.
So you know whether you're getting charge added or not.
Yes.
Yep. Got it.
Ooh.
Great.
Okay. So one thing that the optical microscopy lets us do is watch how the ions are moving. And so what we're going to be looking at here is graphite, which is this grayish blue color. And then as the ions are moving in, you're going to see a wave of color travel through the material. And so that's essentially the ions moving through the material, and they're changing the color of the graphite as they take away or add electrons.
That's cool.
And I saw a cool symbol on there, 50 micrometers or microns.
Right.
Yeah. And
So
those
that's
are
our scale bar.
Cool.
So just tells us how large of a section we're looking at.
yeah.
That is useful.
And that is very tiny as well. That's
Yes.
50 millionths of a meter.
Yes. One thing you'll notice too that we can figure out with optical microscopy is that the ions will sometimes get bunched up in an area, and so that'll tell us if this material would be good for a battery or not, because you don't really want the ions to hit a wall and not be able to get around it and charge the rest of the material. So this will help you identify defects within your material too.
Cool.
using
That's
the
so
optical
cool.
microscopy. And so in our material, the blue is the full state of charge. So that means fully charged if an area is blue. And the colors before that are not fully charged yet.
Cool.
When we were in your lab, we got to see all sorts of cool tools. Can you outline some of those tools and what you use them for in your research?
Yeah, so my overall research is trying to make materials that could go into a battery. And so the materials that I'm trying to make are air sensitive. So in order to run reactions that are air sensitive, I put my reactants together in the argon glove box, which you got to see. I then will either run the reaction in the arc welder, which will heat the materials up and give them enough energy to overcome that activation barrier and to react together. or I'll seal them in a quartz tube using the hydrogen oxygen torch, and then put that into one of the high temperature furnaces and run that for a long time.
Cool.
The third tool that you got to see was the ball mill, which will break our materials into smaller pieces, and also helps us to overcome that activation barrier. And so because you have smaller pieces and you have more surface area where the materials are able to react, you can, that brings down that activation barrier closer to the energy of the reactants, and it makes it easier to overcome.
Cool.
That's awesome. Thank you. That was a great explanation of those tools.
You use tools too.
Can we talk a little bit about some of the tools that you use, Madeline? Because that's the other side. So you have developed these materials, but then of course there's the testing of those materials. So what are some of the tools that we got to see in your lab and how you use them?
Right, so what I do is try to characterize the materials that our lab is making. And so one thing that we really need to have is a device that will allow us to actually look at what's happening to those materials as it's charging and discharging. So what I made was a device that would allow us to do that, and then once we have that device that's made, we take it to our optical microscope and we can look at the material charging and discharging.
Lauren and Madeline, thank you so much for welcoming us to your lab today.
Thank you.
We learned a lot.
Yeah, it was such a pleasure to visit the Warren Lab and see a little bit of what y'all are doing to help kind of solve this problem of how do we build a better battery.
Yes.
So cool.
Thanks again, and stay tuned, viewers, for our Q&A right after this.
Yep, live Q&A.
Woo!
We'll be talking with Lauren and Madeline. See you
Bye.
So awesome. That was incredible. Some really, really high temperatures was some of the things. Like, I mean, they were just kind of tossing these around, but like 4,000 degrees Celsius is crazy hot. Yeah. So I would love to hear some of the questions that our folks students had in the chat. So if you wouldn't mind, Miss McLeod, would you call out some of the cool questions that were asked?
Absolutely. The first question, sorry, I'm scrolling. What materials are used?
Yeah, so we use lots of different types of materials, and we're making new materials using ones that are already made. So the materials that I'm working on typically consist of scandium metal or yttrium metal, various metals, and then also carbon. So graphite, like what is in your pencils, is also used a lot, and we combine those together to make different materials that haven't previously been made.
What is a chemical reaction?
Yeah, so a chemical reaction is when you take two chemicals, which chemicals make up everything that we know. So like water, for example, is technically a chemical. So it's made up of hydrogen and oxygen. So you take two chemicals or even one chemical and you make it into something that it's not, either by combining chemicals or by breaking them up based on their chemical equations, which they're basically all made up of elements, which are on the periodic table.
And you have to heat those things up, like all of those, like when Steve was just talking about, heat it up super, super hot so a chemical reaction can occur, so that, you know, we can see that change. It can break down or combine, or the things that you just said, we can see it. Ooh, someone just asked how hot.
Yeah, so that really depends on the chemical reaction that you're doing. So some chemical reactions will occur naturally. So you don't actually have to do anything to them, and the chemical will turn into something else over time. Some take a lot of energy to occur. So like the reactions that we've talked about, heating together yttrium metal and carbon, for example, both of those have really high melting points. And so we have to put them into an environment that has a really high temperature. So that's why we use the arc welder to do that reaction, because it won't occur naturally. And so, you know, they can span anywhere from room temperature, even lower than room temperature, to 3,000 degrees Celsius.
Right, like water, for example, when it's in its frozen state, like ice, it'll just melt in your hand. But if you held a piece of yttrium, it would feel like a piece of metal at room temperature. You have to heat it, you know, several thousand degrees above room temperature to get it to melt like an ice cube would.
And then what are the elements?
Yeah, elements make up everything. And so depending on like what you're, you know, interacting with, it's probably made up of some combination of elements. And so elements have been studied for hundreds of years at this point, and they are found on the periodic table. And so if you were to look at the periodic table, there's somewhere around 150 elements, I think, on there. So there's lots of different elements that make up, that it can be combined in lots of different ways and make up the world that we see.
I actually have a question for Madeline. We saw you testing some materials by running ions through them. And I was wondering if you could talk a little bit about why the materials that you test, and then why you know, run electricity and ions through them, and then what kind of batteries are you testing materials to be in? Are they like AA batteries or car batteries or cell phone batteries? Can you answer those? Can you clarify some of that for me?
Yeah, that's a great question. So, so when we're doing our devices, we have our material that's made up of different layers, and then we have ions that somehow need to get in between those layers. So how Lauren was talking about, we want that reaction to happen. So we actually need to force the ions through by running a current into through our material. So what that current does is it charges the graphite. So it gives it a positive charge, and then the negatively charged ions are then attracted to the graphite, and they'll go into the layers of the graphite. So the applications that the batteries that we're looking at would probably be more along the lines of like improving your cell phone battery, or trying to do it more for trying to find good materials for other batteries like electric vehicles, things like that. So where we really need to, like, for example, what Lauren's working with, just trying to find materials that will let us pack a lot of ions in there and do that reversibly over time. So taking the ions in and out.
So a lot of batteries that need to be charged again and again and again, and also need to hold lots of charge, enough charge to power a whole vehicle.
Yeah.
That's awesome. And I think it's cool that like we kind of imagine, we've kind of gotten used to, I feel like you probably know that you plug in your tablet or you plug in your computer, or you know, but what you're really doing is kind of the end product of the experimentation that Madeline showed. Is she was essentially plugging in this element, you know, or this molecule, you know, a little differently, not just directly into the wall, right? She had that special tool that she was using, but she was plugging it in, and then electricity could flow into it. And that moved these charged particles or ions through the material. And we could see that with a microscope. That was super cool.
I have one more question. When I think I know, I can envision what like a car battery looks like. I can envision what a battery might look like in a flashlight. But what do batteries look like in cell phones and tablets and computers?
Yeah, so usually like what you'll see is it's kind of like a coin. I think usually they use like a kind of like a coin cell, like for battery for certain devices. And essentially what you have is you have your material on one side of the coin and then an electrolyte in between, and then your other electrode on the other side. And it's all pinched together in like a coin shape. And so then you can put that into your device and it will charge and discharge your device. So not all like cell phones have that same type of battery, but that's kind of like a standard one that you might see in certain devices.
Cool.
Yeah, thank you, Marilyn.
Ms. McLeod, I think we have one very important question in the chat.
Yeah.
So I know that you are wearing the latex gloves, but how does that actually protect your hands from getting burned? And how do you not get electrocuted with all of these chemicals and molecules and everything being mixed together?
Lab safety is so important. How do you maintain
Yes.
Yeah, so for getting electrocuted, that's actually really important when we're working with like devices like the Arc Welder that Lauren was showing, and then also the potentiostat that I was using. And one thing we have to make sure is that we never actually like complete the circuit. So when Lauren's using the Arc Welder, she'll always make sure she has one hand on something that's not conductive. So she's not like actually letting the current pass through her body in case it were to complete it. But there are also, just like not touching the like live wires when current's being passed through is one big thing. And in terms of not getting burned, when Lauren's working with something that's really hot, or I am, we actually have like gloves that are heat resistant. So that really helps us when we're dealing with stuff that's really hot. We don't make sure we don't just wear the latex gloves. We wear ones that are heavy duty. So that's kind of how we protect ourselves.
Yeah, I hear you kind of saying two things. One, you are really careful. You've learned how to use these tools and these materials safely. But then secondly, you also have some specialized tools that help you do that. Yeah, that's cool.
And also in the video, I noticed that you were wearing, a lab coat, and you were also wearing eye protection. You have a lot of different ways to protect yourself, like gear and other things. And also there was like that curtain that also helps other people in the lab stay safe and protect their eyes. Can you talk a little bit about how that curtain protected people's eyes?
Yeah, I can answer this one. So that curtain protects from UV light. So when we heat the materials, or we're using the arc welder or the torch, the heat actually produces UV light, which is the same light that the sun is producing. And we all know we're not supposed to look directly at the sun because that type of light can hurt our eyes. So there are special glasses, one that we have, that protect from UV light, and that curtain does the same thing. So it does the same thing as like glasses. If you've ever worn special like sunglasses that protect from UV light, they have this material inside of them that protects your eyes from the harmful light. And so that curtain does the same thing. And along with that curtain, we also have glasses that we wear when we're actually heating things up with these tools, and that protects our eyes from that harmful light.
So
and
cool.
what about, I guess, protecting your, with the chemicals and breathing, inhaling the chemicals? How do you protect yourself from that sort of thing?
Yeah, so you saw when I was showing the torch that we kept it in a hood, which is kind of a box that has a glass protector in front of it. And so those are built to actually suck gas up in them. And so if you're working with a chemical and you have that glass thing pulled down in front of you, it'll actually pull the harmful fumes into a vacuum-like system away from your body so that you're not breathing in harmful chemicals.
So cool.
Yes, so cool. Thank you, Madeline, and thank you, Lauren, for answering all of our curious third grader questions in our chat. Thank you to Miss McLeod's class from Parkwood Elementary for hosting us this morning. I had so much fun. And thank you to the Warren Lab at UNC Chapel Hill. Thank you again to Willow Austin Soha and Dr. Linda Tergarian, our DPS science specialist. And one more shout out to Parkwood Elementary. Woohoo! Thank you again so much. Steve, will you tell us where we're going next week?
Yeah, next week we are going to be visiting the Durham Bulls Athletic Park. I am so excited to share with you our trip to the field, of course. But really, what we went to do was we went to meet the amazing team of folks that you wouldn't typically see on the field during a game, but they're just as important as the players to producing the kind of Durham Bulls baseball experience that we expect as fans, and that so many of us in Durham and beyond love. So we'll have a chance to explore all sorts of cool behind the scenes parts of the stadium, from the kitchens to the locker rooms and all sorts of interesting stuff in between. And along the way, we're going to see the passionate work and the amazing people that keep it all going, even in the off season. Can't wait to show you. We'll see you there, friends.
See you there. And thank you, Steve, for being such a wonderful host.
Oh, you're a wonderful host. Thanks, Jenna. Thank you, Lauren.
Thank you guys so much.
No
you are
problem.
so welcome.
See you next
Thank
week.
you, Ms. McLeod. Thank you, Parkwood. So curious.